Okay. All right. We've got multiple types of instructions. There's basically 5 groups of instructions, and there's a lot of instructions that we're going to be looking at for the assembly language. As I said, we're going to be moving into C probably about the halfway through the semester, or a third of the way through the semester. Well, actually, we're close to a third of the way through the semester now, aren't we? You know, there's 14 weeks of the semester, and we're into week 3, so probably about halfway through the semester we'll move to C. That's there. Okay, there's 5 different groups. We'll talk about all 5 groups right there. The first one is obvious, the arithmetic. Those are things like add, subtract, multiply, divide. The next one is logical. That's and or XOR. Those are those Boolean functions that you learned in your basic digital course. We can do them on up there, and there's plenty of places where we want to do that up there. We've got data transfer. That's our move instructions. That's about all we've been doing so far has been moving, right? Up there. Boolean variables, where we can go through and do some Boolean operations, and then program branching. That's our jumps and our calls, right there. Those are our 5 groups there, and if we look at the index, we can get the whole list up there. Now, the difference between a RISC processor, which is a reduced instruction set processor, like the PIC, which is another company, Microchip, puts out a processor called a PIC, is that it has a very small instruction set. Then we have a complex instruction set computer that there, which is like this, which has a much more robust or larger instruction set. So our instruction set is relatively large. The larger the instruction set, such as the 8051, the 8086, or the general Intel processors, the easier it is to write code, because we have more instructions to do what we want. If we have a reduced instruction set like the PIC, for example, it's only got 24 total instructions, then it's very difficult to write code. So we've got a lot of different instructions to look at here. And if I'm going to go to index H or A, but it gives the entire reference. I'm just going to kind of flow through here. Arithmetic instructions. The first one is the add. Not there. You know, you're going to be asked to write code where we add some numbers right there. And again, we can use it with multiple types there. The add almost always uses the accumulator. They execute in one instruction, except for the increment data pointer. Remember I mentioned the data pointer? There's a command for incrementing the data pointer. That requires 2 instruction machine cycles. And multiply A and B, which requires 4. That's there. Note that one machine cycle takes 1 microsecond if it's operating at 12 megahertz clock. That kind of gives you an idea how fast this thing will do that there. So we're running at 12 megahertz clock. Our processor is running at 24 megahertz clock. That's roughly what we're using. So it takes about half a microsecond per machine cycle right there. So that gives you an idea how fast you can do does that there. So the first one is add to A the contents of, and don't ask me what 7p hex is. That looks like a real typo to me, right? But we're assuming that that's the address of our data, although it's not 7p, it's probably 7b. That's there. Add to A the contents of the memory location pointed to by R0. R0 contains the memory location, the address of the data. The fourth one is add to A the data that's in R7. And the last one is add to A the number 35 hex. So there's the 4 basic types of addressing modes that we would use for math instructions, right, for the add instruction. It's fairly straightforward right there. Again, we're not going to worry. There's some examples here. It says the accumulator contains 63 hex, R3 contains 23. The program status word contains 00. What's the hexadecimal comment of that there? Now again, what we're getting into right here is that the accumulator is equal to 63, and R3 contains 23. We add the two of those up. That looks like it's going to be 86, right? The program status word is going to be 5. Why? I don't know. We haven't looked at the program status register. The decimal content, it's just simply converting that 86 to decimal is all that is up there. So that's a very typical question that you would look at. The program register status or the status word that there basically contains there. So again, what the result is straightforward. 86. Some interesting that there are 3. I'm not going to get into that too much. There, what they're saying is the decimal content of C discussion is the fact that it could be 86. Yeah, that could be a negative number is what they're saying. If we're operating in sign arithmetic, the most significant bit is the sign bit, and it's in two's complement. That's why they're going into that discussion right there. So 86 could be a positive number if we're dealing with integer that's between 0 and 255, or if it's going from minus 128 to plus 127, that would be a negative number. And the reason I know it's a negative number, and we didn't talk about two's complement in this class, right? No. We did not get into that. You had two's complement in your digital class, though, right? Did you have it in your basic microprocessor class, talk about two's complement? Not there. But if you're dealing two's complement, find microprocessor, microcontroller, arithmetic, the most significant bit is the sign bit. And when I look at the accumulator contains 86, the fact that that's an 8 there tells me that the most significant bit is a 1. Anything above 80 is the sign bit, or the most significant bit is a 1. And if we're dealing with two's complement, sign numbers, then that is a negative number right there. So if this was if we're doing this addition, we're doing sign that there, we would actually have an overflow, is what we would have right there. And that's why our status word is what it is. We haven't really got into that much detail on this processor yet to look at that there, but this is kind of a trick question. That there is, it's a good one, but when we look at those numbers, we add those and we get the number 86 as the result of that operation. If we're dealing with integer numbers from 0 to 255, there's no problem. But if we're dealing with signed numbers, now we've got a problem because now we've overflowed right there, because our answer is above 127 if we're looking at decimal, or above 7F. 7F is the largest positive number we can do with 8 bits in sign arithmetic, is 7F right there. So here we have an overflow. I'm not going to dwell on that right now. Right there. We could spend lots of time talking about that there. But we get into this discussion right here. Again, this is another one right here. This is a short little program segment right there that we move into the contents of R7. We clear the carry flag right there. So for addition, close one byte right there. Second, clears the carry flag in the program status word right there. And then we subtract from the accumulator the contents of R6 that's there. And then we move A back to R7 that's there. So what we're essentially doing right there is we're subtracting from R6 from R7 and moving the data back into R7. It's a very simple little subtraction. Lots of things happen in our subtraction that there, where we may have to borrow if we have a negative number that there. We will write entire programs on how to subtract two numbers and see what more than 8 bits that there. For right now, all I want to do is just mention the subtract mode, right? Instruction there. I'm just going through the instructions now. Add and subtract are the two that we're looking at there. These all affect the flags out there, and we have to look at all of these in more detail, but the way to do that is with sample code right there. Another one is increment right there. And okay. The increment right there, where we increment a particular memory location, and we can increment various other things right there. We can increment registers, but the INC command just increments it. There's also another command for decrement, DEC, right there. And all it does, in this particular case, we're giving it the address 7F, and we're going to increment that, whatever's in that address. We can also increment the data pointer. We can increment the B register, the A register, R1 through or R0 through R7. So here we're going to move direct, whatever direct happens to be. It could, that there, right there. But that's a memory location. What that is direct. And notice that it uses the word direct. We can define variables in assembly language out there and just use the variable name. So move into what the contents of location direct, increment it, and move it back into direct. That actually, this is for if it didn't have that command, how we would have to do that there. That's all this instruction out there. Just happens the 8051 allows us to directly increment memory locations. That's just part of its many, many instructions up there. Okay. And as I said, we also have the decrement right there, and moved R7, and then give that there. I'm going to kind of skip that second part of that there. And then the 8051 does have a command that does multiply right there, and it just multiplies. And now multiply only works with AB. That there. That there. So the multiply command is very, 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 very restrictive. Is that you normally would only use it with AB. So you have, and the answer is always stored in the accumulator right there. So what we're doing is we have 4A in the accumulator, we have 0B in B, the program status word right there, and you compute the answer, AB right there, product is going to be equal to that there, and this is a kind of a tricky thing. It's when you multiply two 8-bit numbers, you can get a 16-bit number. And this is where the multiply command is interesting here. So the high byte is placed in B, and the low byte is placed in the accumulator. So you can end up, when you multiply two 8-bit numbers, the result can be up to 16 bits. So this command allows us to store the high bit in B and the low high byte in B, the low byte in A. So it does that there, and that's why it's limited to just A and B. Right there. Now, the original 8085, 8080, the Z80, a lot of the early 6502, they did not have multiply commands. A lot of the very early microprocessors did not have multiply commands. It really wasn't until the 8086 came out that the multiply command came out, and then the 8051 as a microcontroller had the multiply command. Before you had to write a little code to multiply numbers by sequentially adding. The multiply command was a relatively new feature of this microcontroller. That there. So again, we have some examples on that. Again, I'm just kind of going over these instructions today. I'm not really getting deep into that there. And I'm sure you've seen most of these with the 8086, right? They're not that much different. Right there. And this gets into that there, and this basically does some things I don't want to go through this example here. This is binary coding right there. That there we won't talk about that there a lot. So that there, let's kind of look at the logical instructions. This is logical and, Boolean, and, or, exclusive or, and not. This does this by a bit-by-bit operation. So it looks at each bit, and what this particular does, and in reality what it does that there is bit by bit, is that we're going to AND it. What we got this? Well, we got these twos here for right there. This is is illustrated the immediate data. Boy, lots of typos in that there. So, because this should be a 1, these two should be 1s, is what they're saying. Essentially, when you do a logical AND, all you're really doing is clearing bits that are 0. So if we look at A and L, if A includes 1, 1, 0, 1, 0, 1 right there, if this is a 1, this is a 1, that's a 1. This is a 1, and this is a 0, that's going to be a 0. 0, 0. The only place you get at there, and what you're basically doing is you're just clearing the bits that are a 0 in the immediate data right there. So every place, so what this command here, it's going to clear this bit, clear this bit, clear this bit. If the data has a 1 there, it's going to leave it alone. That there, if it has a 0, it's going to leave it alone. But all it does is clear those bits one by one. If you use the OR, you're going to set bits. That there. And the logical and ORs are not as critical in the 8051 as they were in the 8086. And the reason is the 8086 did not have set byte and clear bytes commands. So if you wanted to clear a particular byte in the 8086, you had to use the AND function. With the 8051, I could just use the clear. So it's not as important of an instruction with the 8051 as it is with the 8086. The 8086, if you wanted to set a particular byte or bit within a 8-bit word or 16-bit word, you had to do an OR function to set that bit. That's how you would set that bit to a 1, is with the OR function, logical OR. If you wanted to clear a bit, you had to use the AND function to clear that bit. With the 8051, I could just use set bit or clear. And I can clear it directly and not use the AND or OR. So it's not as important as there. And again, all the modes of operation will work with that right there. Now the XOR is one that's very, very interesting, because the exclusive OR actually, what it does is it complements anything that's a 1 right there. So it's a very interesting command, is that it does a quick invert each bit. Up there. So the XOR, and let me kind of point up there. My throat is winding out down there, out there. But let me just kind of right there. If I've got the accumulator, let's say it's equal to 1 1 0 1 1 1 1 0 right there. That's what's in the accumulator. And if I XOR that, XRL, if I XOR that with 0 0 0 0 1 1 1 1, what I'm going to do there is, when I do the XOR here, this is an XOR, is I'm going to complement these here. 0 and 1 XOR is what? 1. 1 and 1 XOR is 0. 1 and 1 is 0, 0. And 0 and 1 is going to be 1. 0 and 0 is 0. 0 and 1 is still 1. And 1 and 0 is still 1. Now notice that these 4 bits are not changed. Right there. These 4 bits are complemented. Right there. In other words, I've reversed them. So when I do an XOR, I complement by bit. So by XORing this with 0F, I complement the lower 4 bits, but leave the upper 4 bits unchanged. So it's a very powerful command if I want to invert bits. And there are plenty of times in which we want to do that. That there. So that's where the XOR actually comes in very handy right there. So it's, and keep in mind that how do we find the 2's complement? We complement it and add a 1, right? So an easy way of converting a number to negative is I just XOR it with FF and then add 1. That there. And that converts a number to negative right there. I think not so much because I'm out of material, but because my throat is starting to give out on me. I'm going to let you guys off the hook. I know it breaks your heart to get out of here early, right? No one's commenting on that, right? That's there. So remember, I will not see you next week at all. Not there. Not there. So I will not. Yeah, the Thursday group I will see next week, but this group I will not see next week. That's there. Tuesday we will not have class. I will be at headquarters being indoctrinated into the ways of UniKL. That's there. I have no idea what they're going to do to me there. Hopefully it doesn't involve waterboarding or torture or something like that. But my guess is that they're telling me the things I'm not supposed to do that I'm probably already doing, and telling me the things I'm supposed to be doing that I'm not doing yet. But that's there. And of course, as every good employee, I'll probably listen to about half of it, right? That's there. That's there. Keep in mind that I'm an old guy. I've been doing this for a long time, so getting me to change my ways of behaving might be difficult.